to prove that this point is valid, we are going to be doing an experiment which indicates that boiled water inside a bucket will transfer its energy into a bottle and a balloon attached to it. The balloon and the bottle act as a system, and the boiled water will be the surrounding. Energy is being transferred from the surroundings into the system in the form of heat, and it's equal to delta E, which in this scenario, delta E is equal to Q plus W, where Q is equal to heat and W is equal to work. So once boiled water is added to the surroundings, it will create a temperature difference, and in this case, T1 will be our surrounding and T2 will be our system. And T1 will be greater than our T2. And to reach thermal equilibrium, heat will be transferred from the surrounding to the system. As heat is absorbed by the system from the surrounding, it will cause the water bottle to expand and in turn cause the balloon to inflate. And this is all done in the form of work. So in conclusion, this experiment provides evidence to support that for the first law of thermodynamics, energy is not created but in turn transferred.
This experiment will be viewing the transfer of energy and how energy is not created or destroyed, but in turn transferred into the system. Our system will be defined as the water bottle with the balloon, and the surrounding will be defined as the bucket with the boiling water. Alright, so as I put this boiling water into the surrounding, the system will begin to expand and do work on the system. Okay, so here we go. So as you can see, the heat from the surrounding is being transferred into the system, and the bottle is performing work on the balloon. So the transfer of heat is going through the bottle into the balloon and around, and as the unused energy or heat is being released to the rest of the universe, showing that that equilibrium is trying to be met between both the surrounding and the system by the transfer of heat energy. So as work is still being done on the balloon, it is reaching thermal equilibrium with both the system and the surrounding.
The second law of thermodynamics brings in a new variable known as entropy. Entropy is the amount of ways that energy can be distributed, and in simpler terms you can think of it as disorder. So a solid has much less entropy than a liquid, who has much less entropy than a gas, whose particles are able to roam around much more freely. The second law of thermodynamics states that the sum of the entropy of the surroundings and the system is always increasing. In other words, the entropy of the universe is always increasing.
So in the second law of thermodynamics, not only can we determine entropy, but we could also determine if a reaction is spontaneous or non-spontaneous. So in this case, we have a formula or reaction right here of carbonic acid going to H2O and CO2, which is a common reaction in carbonated drinks, such as soda. So our formula for our delta S universe is delta S system plus delta S surrounding. And in this case, the entropy of the universe in spontaneous forms should always be increasing. So delta S surroundings is actually equal to something else that comes into play, enthalpy. Enthalpy is a form of heat in the easier explanation. So delta H S surrounding is equal to negative delta H system over T. T is known as temperature. And delta S universe, which is a new equation, is known to delta S system subtracted by enthalpy over T. So when we're calculating the system and delta H, it is most easily substituted to products minus reactants, which would be the water and the carbon dioxide subtracted by the carbonic acid. So when solving for delta S universe, we will first need to determine delta S system and delta H system. So delta S system is, the units are most likely already found. So the units or the numbers are most likely already found, and the units expressed are joules per mole Kelvin. And these right here, as I set up, is products minus reactants. So we have the entropy of the carbon dioxide plus the entropy of water subtracted by the entropy of carbonic acid. And as well as for enthalpy, which are expressed in kilojoules per mole. Later on, we will convert these in order to get like terms to make sure these add up. So when calculated, these values add up to 188.64 joules per mole Kelvin. And when solved for enthalpy, the values are 19.36, and these are in kilojoules per mole. So now that we have solved for both delta S system and delta H system, we now plug it into our delta S universe equation. Our delta S universe equation will determine whether a reaction is spontaneous or not. So for a spontaneous reaction, usually it is an exothermic reaction, products are released heat, whereas an endothermic reaction usually is a non-spontaneous reaction because it requires heat. And usually for spontaneous reactions, it releases heat because then it adds to the disorder of the universe. So in this case, we have our values plugged in, 188.64 joules per mole Kelvin for delta S system, and subtracted by 19.36 times 10 to the third joules per mole, as I have converted I have converted kilojoules per mole of delta H to joules in order to have like terms so the equation can add up correctly. So at this instant, we're assuming that we're at room temperature at 298 Kelvin. So when we solve for this, we receive product of 188.64 joules per mole Kelvin subtracted by 64.966 joules per mole in order to have like terms so these could add up. So that's 188, I'm sorry. When we do this and add it up all correctly, we end up with the positive value of 123.67 joules per mole Kelvin. And as we have now provided the instance that this reaction is a spontaneous reaction because it favors the product. Due to the reaction of carbonic acid turning to water and carbon dioxide in newly carbonated drinks, we see that it is a spontaneous reaction, but in the reverse reaction, it could be different. So if it's a reverse reaction, it is usually non-spontaneous because it requires energy. It requires a constant input of some sort of energy in order for it to become its original state again, or its carbonic acid state. This could apply to almost any spontaneous reaction. It could be spontaneous in one direction, but non-spontaneous in the other reverse direction.
Usually when we refer to systems in chemistry or closed systems, we see how the laws of thermodynamics are applied to that, how they make sense. But what about for an open system, or for us, like a biological system, living organisms in the world? How do the laws of thermodynamics usually apply to us? I mean, we're pretty ordered and we do have our energy sources, but how do the laws of thermodynamics really are applicable to us and don't apply? So how does the first law come into play when it comes to the laws of thermodynamics and us as a biological system? Well, we don't just spontaneously pop up energy out of nowhere. We obtain it from such glucose molecules or fatty acids when we eat fruit, or when we eat any kind of food molecule. We obtain these glucose molecules from these foods and we use them and exert them as ATP. That's how our body functions, which is how we are able to transfer the energy from these food molecules. Now take the second law of thermodynamics, for example, where the entropy of the universe should always be increasing, disordered. But we're a pretty ordered system, so how does that apply to us? When we eat these molecules, we are able to exert them energy, such as when we exercise, when we run, when we do any kind of physical activity, or even when we're just living. We're exchanging heat with the universe, so we're constantly releasing heat that is unused or we don't really need. We're releasing it into the universe, increasing the disorder of the universe. That's how the second law applies to a biological system and does not violate.